Today we're going to take a look at finding derivatives of inverse trigonometric functions. Now, these functions don't come up a lot, but when they do, we need to know how to take the derivative for them. We're also going to learn how to take the antiderivative for them later. Okay, so a couple of things to remember with the inverse trig functions. First of all, they look like this. Sometimes you'll see this read as sine inverse. Sometimes you'll see it read as arc sine. I have a tendency to say arc sine or arc cosine. And the other thing to remember here, and this is going to be important to us, is that the range here for this function, in order to maintain this being a function, is that y has to be between negative pi over 2 and pi over 2. Of course, that changes with the cosine function and with the tangent function accordingly. But that's going to be important to us as we move through here as well. So we're going to look at this function here. I'm just going to do the arc sine function. The arc cosine and the arc tangent function are very similar to this one. So if you see how the arc sine function is done, you'll be able to determine what the inverse cosine and arc tangent functions are as well. So we're gonna start by taking the arc sine of x equals y. We're going to try and find dy dx or y prime with this. The way that we're going to do it is we're going to go through first of all, and we're going to take the sine of both sides to get rid of that inverse trig function. When I do that, I'm going to find that x is equal to the sine of y. Okay, that's an important piece of information to have to start off with. So now we're ready to differentiate this. This is going to be an implicitly differentiated function because I have the y, which is a function inside another function. So I'm going to have to do this implicitly. And when I do that, when I take the derivative of x, I'm going to get 1. And then when I take the derivative of the sine of y, I'm going to get the derivative of the sine is the cosine. So I have cosine of y, and that's going to be multiplied by y prime, or dy dx. There's my implicit differentiation. So I need to solve this for y prime. To do that, I'm going to divide by the cosine of y. That's going to get me 1 over the cosine of y equals y prime. And when we were working with implicit differentiation in the last video, we kind of stopped at this point. We're going to actually work with this just a little bit more and see if we can find a better formula for this, one that's defined specifically in terms of x. To do that, I'm going to go off to the side here for just a second, and I'm going to have you remember that we had a Pythagorean identity when it came to trigonometric functions that said that the sine squared of y plus the cosine squared of y was equal to 1. That's our Pythagorean identity for trigonometric functions. And I'm going to solve this for cosine of y, and when I do that, I'm going to get cosine squared of y is equal to 1 minus the sine squared of y. And then I'm going to take the square root of both sides. And when you take the square root of both sides for this, you get cosine of y equals plus or minus the square root of 1 minus sine squared of y. But, and this is where this piece of information that we had over here comes into play. Remember that y was stuck between negative pi over 2 and pi over 2, and the cosine function over that interval, that's the first and fourth quadrants, the cosine function with those angles is always going to be positive. So I don't really need the plus or minus here because of the situation that I'm in and the restriction on the range for y. I know that this result is going to have to be the positive value for that. And so now I'm going to go in and I'm going to say, okay, I've got the cosine of y equals the square root of 1 minus y squared, the square root of 1 minus sine squared of y. But notice that the sine of y is equal to x. And so I can replace sine of y here with x, and that gets me that the cosine of y is equal to the square root of 1 minus x squared. Okay? And now I can replace my cosine of y down here and find that the derivative of y, the derivative of the arc sine function, is going to be 1 over the square root of 1 minus x squared. Okay, so there's my formula for the derivative of the arc sine function. Like I said, the derivative for the cosine function and the derivative for the tangent function work very much the same way. They're very similar in that process. So I'm not going to go through and derive those and create those for you. If you want to go through and find out how those things develop, then certainly you feel comfortable to do that. Like I said, they work very much the same way with this one. I am gonna go through and tell you what those are, though. The First of all, we found out that the derivative with respect to x of the arc sine function is going to be 1 over the square root of 1 minus x squared. The derivative with respect to x of the arc cosine function looks very similar to that. The only difference is going to end up being that it's negative. So we have negative 1 over 1 minus x squared. And then the derivative of the tangent function, the arctangent function, is going to be 1 over 1 plus x squared. There's no square root involved in that one. So those are your three formulas for your derivatives for the primary inverse trig functions. I'm not going to worry about developing the ones for the arcsecant, arccotangent, and arccosecant because those don't come up really at all, though we could develop them if we wanted to using our quotient rule. Okay, so those are the three formulas that you'll need. We developed this one. Certainly we could go through and do the same type of thing to develop these last two here, but you'll certainly want to jot those down, make sure that you have access to them. Let's see if we can apply this really quickly. I'm going to take a function and I'm going to say, let's say that we've got y equals the arc cosine of, let's say, 2x cubed. Okay, this function is a function within a function. We've got an arc cosine function. We've got another function inside of it here. And so we're going to have to use the chain rule when we differentiate this thing. We're going to go straight to our formula that we created. That's going to be that y prime is equal to, let's see, the derivative of the arc cosine function was negative 1 over the square root of 1 minus whatever was on the inside of here squared. So I'm going to take 2x cubed and I'm going to square it. That's going to give me 4x to the 6th. Okay, that's my 2x cubed squared. That's my something squared that I was taking the derivative for that for. And then we have to, because of the chain rule here, we have to multiply that times the derivative of the inside function, which in this case is going to be 6x squared. And so my derivative for this function is going to be negative 6x squared divided by the square root of 1 minus 4x to the 6th. So that's the application for this. This is how you would use it using the chain rule. Of course, if you had the product rule involved in here as well, then you'd need to use the product rule, say we had a function multiplied out here. Okay, so this is the derivatives of the three primary inverse trig functions. Like I said, we didn't take a look at the other ones, but they work pretty similar to what the first one was that we proved with the inverse sine function.